Hello, my name is Greg Risterman. I'd like to welcome everyone today to this webinar titled Advancements in Phased Array Probes for Weld Inspection. This webinar will include a live demonstration of Olympus's new Weld series probes and Olympus DMA dual matrix array probes for best practice OmniScan setup and beam characteristic measurements to ASTM 2491. Additionally, phased array probe and wedge parameters and their effect are explained using OmniPC Weld inspection data and Olympus NDT Setup Builder scan plan software. Our presenter today is Chris Magruder. Chris is a global product support specialist for Olympus phased array products. He has over 15 years of experience providing global support training and application development for phased array customers of all levels, in addition to participating in new phased array product development. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not used for Q&A. If we're not able to get to your question during the webinar, they will be addressed personally either by email or phone after the event is over. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, take it away.
Hello, everybody. Thanks for joining us, and thanks for your interest in Olympus phased array probes. Our webinar this afternoon is going to talk about a new Weld series of probes that has been released by Olympus specifically for the inspection of welds. The objectives that we hope you come away with at the end of this webinar are to have provided you with an explanation of the new probes and wedges, their configuration and recommended use, some basic demonstrations of beam checks for A-scan quality and best practice that we use to evaluate all probes and wedges, and what are the key features and parameters that we look for. The new Weld series probes are designed to improve OmniScan and Focus PX weld inspections with fewer, more optimized probes and wedge designs, specifically for welds, but also with the use in a large range of applications as their similar configuration and frequency. There are many OmniScan owners using either the wrong probe or a less than optimized probe for their particular type of weld inspection. Both the design of the new Weld series probes and wedges and the recommendations that you'll see in this presentation for them are intended to standardize and improve this situation with fewer models and more versatile range of use. The new Weld series probes from Olympus consist of two new probe housings, the A31 smaller pitch, smaller probe, and the A32 larger probe. These are in 3 configurations that are designed to cover a wide range of piping bevels for both 16 pulsar instruments like the OmniScan SX and 32 pulsar instruments like the MX2 and Focus. The new probe and wedge designs bring the best of the history of Olympus probe manufacturing and eliminate some historical acoustic and mechanical limitations of the wedge for an improved optimized S-scan inspection. The new Weld series probes has a new housing. The A31 and A32 housings are a smaller, lighter, more ergonomic design as compared to some of the legacy probes from Olympus. And the elements are symmetrical within the housing. The wedge screws do not allow a reverse option, and this isn't necessary because the cable exit design will not interfere with the Olympus scanner mechanics and probe holders. The A32 housing, which houses a 5 megahertz linear 32 element, and another version of twice the elements, half the size, both use the same housing, which is very advantageous because it means they also use the same wedges. The first of the three probes, and the smaller of the Weld series, is the 5L32A31. And for those of you who might not be familiar with the Olympus, that's 5 megahertz linear array, 32 total elements, and the A31, or the last alphanumeric, is a housing that gives us compatibility with the wedges. For accessible welds, where a small footprint is not required, the 5L32A31 would replace the A1, A10, A11 probes for what most customers use for weld inspection for both manual, encoded, and full mechanized scanning. And for mini welds, it will also replace or outperform the A2 and A12 for a few reasons we'll explain as well. The A31 is the smaller of the two probe housings, and it's recommended to cover most common weld bevels and pipe diameters in the phased array inspection market and ANSI piping chart. In this presentation and throughout some of the slides, you're going to see some tables with a recommended thickness versus aperture and probe wedge in relationship to either a 16 pulsar or 32 pulsar instrument. We'll explain these in a little bit more depth as the presentation goes, but the one point I'd like to make now is use of the compound S-scan, which you'll see shortly and has been released in Olympus's new SUB software, makes it important that we adjust the aperture appropriately for the sound path, because in most of these inspections we'll be using the entire probe all of the time. And this will make more sense as we go. And again, this is a thickness versus aperture, which aperture would be the number of elements times the size of the element, which would be the equivalent of the conventional UT probe's size or diameter. The 5L32A31 is a 32 element probe, and we're recommending this for many customers that would have traditionally bought a 16 element probe like the A10 or the A1 due to a 16 pulsar instrument. So what is the benefit of buying a 32 element probe if the pulsar is limited to 16 element apertures like the OmniScan SX? When using the compound S-scan, there is enormous benefit. An example below, the 5L32 compound S-scan on a 12 millimeter V weld results in more coverage, a higher probability of flaw detection. The inspections, even on thicker welds, will typically be done with the probe as close to the weld as possible, meaning that we're not backing it up for coverage. And it provides the same flaw characterization typical of a standard S-scan as compared to a pixelated or a grainy linear or E-scan. And again, the compound S-scan, we have a dedicated webinar next Tuesday regarding setting up the OmniScan for this, but it's still an S-scan and it works exactly the same. The only difference is we're spreading out focal law first exit point and focal law last exit point throughout the probe. So even in a 16 pulsar instrument, we have great benefit by using a 32 element probe. The 0.6 millimeter pitch of the A31 or 0.5 millimeter pitch of the 5L64A32 will have a little better beam steering as a result of their smaller elements than that of any 1 millimeter pitch probe like the 5L32A32 or Pipe Wizard or A14 probes. The sound path distance, size of the calibration target, or side drilled holes or notches, the size of the aperture, the total number of elements, the focus, and the angular range will all determine the SNR probe limits for any scan plan or weld bevel. And before we continue with more examples of the data and the probe's recommended use and features, we wanted to spend a minute showing you some basic beam checks on how we validate probes and what we look for on any probe or wedge, whether shear wave pulse echo or longitudinal. So what we're looking at now is a compound S-scan from 40 to 72 degrees, which is the typical range of what the shear wave probes and wedges are capable of. And we're looking at a side drilled hole at 25 millimeters in depth. Okay, on the clock, not on the encoder, we're taking a clock scan of a side drilled hole, exposing it from focal law or A-scan first all the way to A-scan last. And we're looking for several unique features that will expose the setup as either valid and exiting the wedge with appropriate beam acoustics or outside the range of the physics or the probe. This is a setup that we have calibrated for sensitivity that we can see in the C-scan, but we have not done anything to modify the wedge delay or made any tweaks. So we're coming right out of the calculator with regard to time of flight. So at the nominal wedge angle of 55 degrees, we want to take a look at the side drilled hole. The clock scan was acquired with the envelope on. So in analysis mode, we have the ability to create the envelope signal. At the peak amplitude, we're looking at the correct depth of 25 millimeters. And again, this has already been calibrated for sensitivity using the wizard so that all of the A-scans are at the same amplitude of 80% or very close. When I take the data cursor or do it live on the block, the first thing I'm going to look for is my ability to maintain the correct depth at focal law 1, which is the 40 degree here, all the way through to the nominal wedge angle. We're looking for the center of the energy directly in the middle of the target at the correct depth calculated by the trigonometry for the amplitude signal in gate A. And then we're also going to take this all the way over to the last focal law, in this case, 72 degrees. The envelope signal allows us to see the peak data and peak up the signal. So in this case, the trigonometry is correct because the angle is correct. And we can do that for all of the A-scans throughout the S-scan. So our very first indication is ability to maintain correct angle, trigonometry, and beam shape on both sides of the sector scan. Correct depth. Again, we're already calibrated for amplitude. And in addition to the trigonometry, we're also looking at the size and the shape of the side drilled hole. Is it elongated? Is it symmetrical with the beam envelope? Is the energy in the center at the correct position? These are our first indications of a good setup, or a setup where we have not exceeded the beam steering limits of the probe. With that simple check that can be done on any side drilled hole or calibration, in some cases even a notch, what we have validated, what we know right now before we continue, is that the velocity of the wedge, the velocity of the material, the height of the first element of the wedge angle, and the acoustic beam steering limits of this probe, wedge, and setup are all valid. It would be impossible to maintain that hole at a constant depth with this precision if any of those variables were out of tolerance. Anything we do for wedge delay after having proved this is only for a compliance reason, not to improve the acoustics. And in this case, the wedge delay wizard would be much better to just accept it within tolerance than making any changes to it. Now, The next part of this is the envelope signals that we see here under the select readings envelope. These are -3, 6, 12, and 20B in a dB. In a manual inspection or a raster inspection, when I can move the probe in and out from the weld, that doesn't mean very much. In a one-line scan where I can only see the weld from one position, this is a very good indication of the vertical height sizing window, also called the echodynamic. This will tell us if our sizing accuracy on the weld bevel and in the weld volume is going to be useful. All of these parameters and the precision, the dynamic range of how wide I'm able to make the S-scan are affected by the probe frequency, the size of the elements, the number of the elements, the size and depth of the target you're using to validate them on. In short, everything. And what we're looking for also is an S-scan that is free of extraneous adverse echoes from the wedge corner, wedge dampening, or housing, free of side lobes associated with a poor element aperture configuration. And as we can see here in the 5L32A31 designed for thinner wall components, we have a very high quality beam, calibratable between 40 and 72 degrees. And if we just add the weld bevel, and I'll just enter the thickness real quick so we can visualize the weld bevel. In this case, we're at the edge of a 12 millimeter or half-inch weld on the second skip. So when I'm able to prove this quality of a beam at the edge of the second skip, I know that within the volume of the weld and heat affected zone, I can expect a very good inspection. Any problems with calibration, with a doubt if the angular range is within the capability of the probe, can be validated very quickly and easily on radius and side drilled holes using this technique. And if you do this on your existing probes, you will also learn that it becomes impossible to recreate that precision using less than about 20 or 24 elements of any size pitch. At 16 elements, it's pretty close, but we start to lose it on the low and the high end. The probe frequency, it'll have a great effect on this as well. And it's a very first check that will expose any problems. If you selected the wrong wedge in the database, if your beam selection is outside the working range of what's possible, all of those things can be exposed fairly quickly. For angle beam groups, and again, we're laying the foundation for some of our beam checks that are coming ahead. And I wanted to emphasize a few points as there are common problems and issues with the Olympus customer base. For angle beam groups, the following beam parameters cannot be corrected if a tolerance velocity or tolerance angle range is out in the setup. If you have selected range, angle range too high or too low, if the velocity of your material is not within approximately 25 meters per second of what your real material velocity is, none of these parameters, not the angle, focus, exit point, time of flight, wedge delay, or trigonometries readings can be corrected. Those are all functions of the calculator setup. The only thing this wedge delay calibrator will do is correct wear on the wedge as a result of changing the height of the element. This is the most common scenario for a wedge delay where people would calibrate it. And in this scenario, we can see that the first laws between 40 to approximately 60 degrees are valid and very tight within the tolerance, but the higher angles here are out of tolerance. Okay, the velocity of the material, the excessive beam angle steering outside its range will all have an effect on that, in addition to the actual wedge wear. And problem number one in the customer base that results in this is using a very small aperture, like 16 elements, from the top of a big wedge, traveling so much wedge delay that it deteriorates the beam. The effect this has is it understeers the beam, or our 70 is actually a 68 or 67. Some of the Olympus probes and wedges will allow you to obstruct a 16-element aperture on the corner here, which also has the same effect. So at the end of that, another block that we use commonly, it's very useful for phased array probe and beam validations, is the ASTM 2491 block in different materials, a carbon steel, a stainless steel, and so forth. Regardless of your wedge delay calibration procedure, at the end of it, you should be able to place the probe on the cow block, simulate the index axis position of the inspection, and visualize the S-scan beam and focus throughout the weld volume. Okay, we are looking for correct exit point, correct angle, correct time of flight, and trigonometry so that the flaws appear in the weld where they are supposed to. That translates to confidence in the analysis. When flaws plot on the weld overlay and at the correct depth, it helps us very much perform the analysis. And it will also expose pretenders from contenders for probe wedge combinations. And these basic checks using the A32 and A31 new Weld series probes will validate the improvement in both the probe and the new wedge designs. The second of the probes in the new Weld series is the 5L32A32. Inside the housing are 32 elements of a 1 millimeter pitch, optimized for medium to thick weld bevels, and acoustically the same configuration as our PWZ3 with a much improved wedge design. So it is capable of a large aperture 16 millimeters when used with a 16 pulsar instrument, or a very large 32 millimeter aperture when used with a 32 pulsar instrument like the MX2 or the Focus, for a wide range of general weld inspection. Problem number one with the customer base, doing heavy wall piping, thick ASME 8 pressure vessels, in-service inspection of heavy wall components, typical of the EPRI fossil test. Where customers don't perform well in those applications or fail outright, most commonly is the result of not having the right probe and that not having a 1 millimeter pitch probe. Heavy wall components with 0.6 and 0.5 millimeter probes, even when using a 32 pulsar instrument, are a big compromise in detection, sizing, and overall beam quality. The two probe combination of the A31 and large pitch A32 would give us a very large range of the ANSI piping chart and perform most inspections, even heavy wall thick vessels. And again, we have two versions of this A32 that we will demonstrate the difference shortly. So another data example using the heavy wall 5L32A32 is a 25 millimeter double V weld. Bear with me. A 25 millimeter thick double V weld where we're doing a full skip volumetric inspection. Again, using any pitch probe, it would be impossible to achieve this coverage on the ID and on the OD without use of the compound S-scan. To take a look at a couple flaw samples here, and again, in an area of the weld with no flaws, we want to visualize the weld. Zoom in a little bit. We want the S-scan free of wedge echoes from the casing, the dampening, or the back corner. No interference in our area of inspection. Here, this is a double V weld, so we see a little roll on the ID, and we see another roll on the OD. And when we look at this, the coverage between A-scan first and A-scan last is much different than our standard S-scan, but we still get the flaw characterization quality. Here we see a small lack of fusion in the upper half on the full V-skip near the surface on the near side. And here we see a small toe crack right on the edge at the end of our second skip. So if we zoomed in on this and we rolled back and forth looking for the deepest crack tip, we'll identify it here and place a cursor to represent the deepest tip ligament of the crack. We'll place another cursor on the full skip to the top, and we have a 2 millimeter through wall toe crack on the full skip at about 50 millimeters in true depth, or the full skip of a 25 millimeter weld. Very typical, and again, a 1 millimeter pitch, large aperture probe for long metal paths and thicker components in the range of 25 or 40 millimeters. The large pitch probe is going to help us greatly over a 0.5 or 0.6 millimeter pitch probe, whether using a 32 or 16 pulsar instrument. The 5L64A32 is a 64 element version 0.5 millimeter pitch probe in the same housing using the same wedges. Where the A31 covers the thinner side of the ANSI piping chart and used with the big element pitch 5L32A32 for heavy walls, this probe is a high performance probe designed to be used with a 32 pulsar instrument, although it's still compatible with the 16 pulsar instrument, for a wide range of the most common size piping in the range of approximately 12 to 25 millimeters. In this data sample is a two-sided coverage of a 12 millimeter V weld. The A1 and A10 are not capable of this inspection due to the number of elements limitation, and the larger element, A2 and A12, are not capable of this inspection resolution for acoustic and mechanical limitations of the big wedge. An example of a data file acquired with the 5L64A32 would be a duplex weld such as we see here. This is a 12.5 millimeter V weld using a compound S-scan from 40 to 72 degrees and we can see the coverage on the ID is more than enough to satisfy a typical B31 heat-affected zone or EN type HAZ requirements. And on the full skip to the cap, we see enormous amount of coverage. One of the primary benefits of the compound S-scan is that it's performed with the wedge right up against the weld toe. We do not have to back it up for coverage. We see on a clean section of the weld with no flaws, no extraneous signals from the wedge. Sometimes the customers don't identify these as wedge noise, just nuisance in their S-scan. But very different than some of our competitor or some of our previous probe and wedge designs for common aperture. In this case, it's a austenitic weld, and we can still see very good A-scan crack characterization. We would expect precision sizing similar to a standard S-scan with added benefit of closer inspection to the weld and greatly improved coverage. In this case, here is our small crack tip. We'll zoom in on this, update the A-scan. We'll put one cursor right on the tip of the crack and another cursor at B0, representing the through-wall dimension for the overall through-wall dimension of the crack. The 5L64A32 would replace the A2 and the A12, and in many cases also the A1 and the A10. Where we don't need a very small wedge footprint for smaller welds, and where we don't need a 1 millimeter pitch element for very long sound paths and heavy wall piping in vessels, the 5L64A32 is our premium inspection with the new Weld Series wedge in the most common range of weld thickness between about 12 and 25 millimeters, and is inherently uniquely qualified for B31 piping inspection. So what is the advantage of the 5L64 or 64 element version of the A32 as compared to the 32 element version of the A32 when used with a 32-128 instrument? Okay, although there is compromise on the thin side due to wedge and the thick side due to element size, again, in this thickness range and a little above it and below it, for typical refinery piping and pipeline inspection, it provides best overall inspection and coverage. Additionally, it provides the most versatility for widest range of bevels if sale is only limited to one probe or one job within its narrow thickness range. And again, in this example of standard V-weld of 25 millimeters, we see the aperture chart telling us that a 16 millimeter aperture is appropriate for this thickness and weld level. That can be achieved either by a 32 times 0.5 millimeter 64 element A32 or from a 1 millimeter times 16 A5L32 A32 using the larger pitch. Some of the probes that were not updated to the new Weld series was the A10 and A1. These are very common probes with very high level of customer satisfaction. These are still available. They use the SA10 version of this, uses the aluminum I8C housing, And one of the benefits of this probe wedge using the I8C aluminum ring is that it's less dependent on the AOD curvature needed for smaller diameter pipes. Why is a 16-element probe like the A10 not available in the new Weld series? These were very the satisfaction level was already very high with them, and in most cases people purchased this probe because their instrument was limited to a 16 pulsar instrument. There is a very big benefit to using a 32-element probe like the A11 or the new A31, even when the pulsar instrument is limited to 16 pulsars at a time. And the reason for this is use of the compound S-scan. It's very beneficial. Many customers that were doing standard inspection with this probe using a 16 or 32 pulsar instrument would have been better off and gotten a better inspection with more coverage by using the 32-element versions. They still have a small wedge, so they're still extremely useful. But for those reasons, the A1 and the A10 are still available for where a very small footprint is needed. That's on the low side. On the high side, we also did not update the large element count 5L60 PWZ1, which would also be similar to the 1 millimeter pitch A14. For 32 pulsar instrument owners that primarily perform piping and vessels inspections on welds over approximately 40 millimeters, the Pipe Wizard PWZ1 5L60 will provide more coverage than the 5L32 A32 of the same pitch. The PWZ1 probe and N55S Rev C version of its wedge is one of the most reliable probes available from Olympus with the longest track record of success. The downside, it's got a very big wedge. The upside is it's a deep penetration vessel and heavy wall penetrator with much coverage. In this example, we have a 40 millimeter weld bevel from very close to the weld using an S-scan from 40 to 70 degrees. We're getting very good coverage. And again, in the aperture charts, we will see this appear for the over 40 millimeter versions, but based on changing the aperture within the probe, it is still very useful for a wide range of coverage, even down to 10 or 12 millimeter thick welds. And in this case, we see that same probe on a nav ship block with the side drilled holes 50 millimeters apart. We can see 1, 2, 3, 4 of them. We would never achieve that level of coverage without use of a compound S-scan, and this is all within the calibratable range and beam steering limits of the angles between 40 and 72 degrees. So just as important as the new probes, and in some respects more important, are the design of the wedges that go with them. The new Weld Series A32 and A31 wedges use an all-Rexolite design that provides an isotropic constant velocity with minimum frequency filtering. That's the benefit of Rexolite and why most manufacturers use it. Like most shear wave wedges in the Olympus catalog, the new Weld Series wedges are designed to produce shear wave angle beams of approximately 40 to 72 degrees with a beam exit as close to the weld as possible for common apertures recommended in the aperture charts. I8C or scanner options include the integrated scanner ports directly into the wedge, irrigation ports with more efficient piping to create a little puddle of water under the wedge for improved coupling, adjustable carbide feet, and new integrated wear plates. The integrated wear plates will prevent wedge wear for a more precise, repeatable inspection and it improves our results, especially when used with automated scanning and raster scanning. These will save the wedge wear, improving our wedge delay accuracy. The new A32 and A31 Weld series wedges are not compatible with the aluminum IC rings, and the all-Rexolite design is intended to overcome some mechanical and coupling problems that were associated with the large versions of them. The primary problem on large versions of these that was not a reported problem on the smaller versions were the coupling and instability on smaller diameter piping with large probes, excessive weight from the big probe models like the A14 that had some repeatability issues at 9 and 3 o'clock if not controlled very well by the operator and using the appropriate springs and number of springs. So on any wedge design, there's many considerations, but the primary three are the nominal wedge angle that generates either a refracted or longitudinal beam, optimized for the middle of the desired S-scan angular range. For Olympus, that's normally N55S or N60L. That means a nominal shear wave 55 in carbon steel. Okay, the height of the first element. This is a compromise between clearance and beam formation for different apertures. It has a very important effect on longitudinal beam pulse echo wedges that we'll see in a couple slides. The larger this parameter, the more wedge delay, and this can be used either to avoid adverse echoes from the wedge and probe housing, and this is also optimized for the element size, the typical aperture size used with the 16 or 32 pulsar instrument, and propagation mode of either shear or long. The third parameter for consideration is the beam exit offset. We want the high angle exiting as close to this corner as possible for common probe apertures without interference from the dampening and without extraneous signals from the wedge corners. Okay, we want this as close to the weld as possible for maximum coverage on the first leg. There are Olympus probes and wedges that will allow the operator to program a beam that obstructs it partially because of this corner. And that's okay as long as the operator is aware of it and can move it back a few elements. So all of these three design parameters and many others were taken into account using the best and worst of Olympus probe manufacturing to overcome some of those issues for a better design. In this slide, we're comparing the elementary A-scan of the A32 wedge design versus an older model using a standard setup that we use both to validate that the elements are active in the probe and the pulsars are active in the instrument. We do a one element step E-scan, meaning that every element has its own independent A-scan. There's no grouping them together, no beam steering, and no angle. We program the setup with a contact wedge, meaning no wedge, and we enter the material velocity for Rexolite. So in fact, we're essentially inspecting the wedge with a single element A-scan. Looking at this and turning up the gain allows us to see some interference from the wedge corners, noise from the dampening or probe housing. In an optimized wedge, and by the way, the one wedge could be perfectly optimized for one aperture, but selection of another aperture might cause adverse effects. Before you get to that, we can evaluate the wedge just again on the basic elementary A-scan of single element linear scan. here. Here we see this is the bottom of the wedge, and this is the entry signal, and we can see it's free of extraneous signals. It's clean and clear. We have an amplitude shift as the time of flight is increased, and all the indications of a very good wedge. In some other models, or using a configuration that pushes the limits of a wedge design, we can also here see noise. This noise amounts to interference in our S-scan. Most customers don't have the reason to trace where it's coming from and why. It just interferes with the inspection. There's many different wedge echoes that can be eliminated or reduced, that we see in some configurations are directly impeding or interfering with the inspection. All of these, and what Olympus learned in the last 8 or 10 years of probe manufacturing, have been taken into account in the new Weld series. So in the wedge angle, again, we use a nominal 55-degree shear wave in carbon steel, and to generate that, we use a 36-degree wedge cut on the wedge. For a longitudinal beam, we would use a much lower cut that causes more wedge noise in addition to a shear wave beam and echoes from the housing and corners. The extent that the beam can be steered above and below the nominal wedge angle is directly related to the probe's element size, frequency, and aperture. The smaller the elements, the better the beam steering. The SNR of the S-scan angular range, meaning the difference between the A-scan first and last for a sensitivity wizard, is approximately 20 dB, meaning that in between the 20 and the 40 and 72 degree A-scans, they cannot be separated by more than 20 dB if they hope to clear the calibration intolerance. So if we were to change this angle from 36 degrees, we could improve the low or the high side beam steering, but we select a 36-degree wedge, so our 55 represents the middle of the S-scan for optimized beam steering. The second parameter we discussed, the height of the first element, affects pulse echo shear wave wedges much more, or pulse echo L wave wedges much more than the shear wave. The height of this is increased so as not to cause a reflection from the elements bouncing back into the probe housing or top of the wedge, because this uses a lower angle. At 20 or 23 degrees, we must increase the height of the wedge. Now, L-wave wedges in general extend the use of an OmniScan and probe, but are far exceeded by the use of the DMAs, dual matrix arrays, that we'll see shortly. The new Weld series L-wave wedges are designed to have an element height that is optimized to provide a 16-millimeter inspection depth for the smaller A31 probe and a 90-millimeter inspection for the larger A32 probe. These are always going to be a compromise between height of the element and interference from the wedge at some depth. And again, within the advertised range, we see a very high quality S-scan free of some of the adverse wedge echoes in earlier models. The DMA matrix array probes are overwhelmingly recommended for any L-wave application now. As soon as you separate the transmitter and the receiver, it removes all wedge considerations from the equation, including the height of the first element, wedge dampening, all of that goes away. And these can be calibrated to a much greater dynamic range because they're not losing so much energy from the wedge, and we don't have nearly the effects of the wedge echoes with the big pulse echo wedges. And what that amounts to is a optimized inspection with a much shorter time of flight through the wedge for CRA, austenitic, and coarse grain materials that are very difficult to penetrate. Again, these will far outperform the L-wave wedges of pulse echo probes. And then our last consideration is the beam wedge exit. Again, we want this exiting as close to the corner of the wedge as possible without obstructing the beam that results in understeering and a correction in the wedge delay calibrator. In most of our cases, we want as much coverage on the first leg as possible with the probe as close to the weld as possible for better results. Wedge echoes from the corner of the wedge, and again, some of the probes and wedges, depending on the aperture that is programmed, allows the operator to create a situation where it's obstructed. This can be reduced or eliminated by changing the aperture or moving the aperture back a few elements from the probe. In some cases, these can't be eliminated because they come from the probe housing or from the back of the wedge. Most customers wouldn't recognize this from what it is, but know it interferes with their inspection and causes them problems in their calibration, and we'll see a big improvement. The recommended probe wedge apertures in this presentation. By the way, everybody that registered with a valid email address will receive a copy of this presentation and the data files that were demonstrated, so you need not to screenshot it. That'll come shortly after the email blast at the conclusion of the webinar. But within this presentation, the probe recommendations take into account beam size, beam exit point, and sound path for typical weld bevels in the ANSI piping range and above it. The limits of these probes are always pushed by customers, and recommendations are estimates that can only be validated through trial and error in real inspection conditions. Lack of a 1 millimeter pitch probe in the toolbox for thick welds, including people that don't perform well on the EPRI-FOSSIL qualifications, is problem number one for most customers performing heavy wall, vessel piping, and in-service inspection. The charts for the aperture recommendations don't list any S-scan angular range or focus other than the nominal angle range advertised with the wedge. They do not differentiate when the inspection is supplemented by TOFT or not, and make no specific recommendation as to exact scan plan. But all of those are taken into consideration for a typical 40 or 45 to 65 or 70, 72 degree scan plan. So in other words, they are a starting point and guidance for thickness versus probe aperture versus probe. With use of the compound S-scan, 24, 32, 28, 16 element apertures will be commonly recommended, where previously that 16 or 30 pulsar instrument was the limitation for how most apertures were selected. It's no coincidence that these apertures are very similar to conventional UT probe size for a given the thickness or weld. In conclusion, again, the new Weld series probes, designed for the widest range of use for most weld customers and any application, in fact, even beyond the welds, are the A31 and A32 probe housings in 3 configurations. The larger A32 probe comes in a 1 millimeter 32 or a 0.5 millimeter 64 element configuration for the widest range of piping bevels. The standard frequencies for all of these in carbon steel is 5 megahertz, but they're available in other frequencies as well. The new probe and wedges designs bring the best of Olympus probe manufacturing experience and eliminate some historical acoustic and mechanical limitations for an improved optimized S-scan inspections. With that, I want to thank you for attending our webinar. Be sure and contact your local Olympus salesman or distributor for pricing and lead times. There were some questions in the chat that will be answered in the email blast that will include this presentation and the data files that we saw during the presentation. I want to thank everybody for attending, and I'm going to turn this back over to our moderator. Thanks again.
Thanks, Chris. On behalf of Olympus, I'd like to thank all the attendees for joining us and Chris for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar, along with a Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for this event, whether you attended or not, will receive the follow-up email with links to the archived presentation and links to the data material that Chris alluded to earlier. That's going to do it again for today, and thanks again for attending. We will see you again next time.